Hi guys, this is a re-recording of question number 1 from tutorial 2 since we couldn't record it during class. So what I'm going to cover in this recording is first I'll talk a bit about camera projection and the pinhole camera model, and then secondly I'll talk about camera calibration, and finally I'll talk about how you can take a 3D point that's defined in the camera coordinate frame and how to kind of transform it to the 2D image coordinate frame. Right. So first let's talk about the pinhole camera model and camera projection. So this material was also covered in your class, but I'm just going to quickly run through all of it because it's easier to explain camera calibration once we discuss this. So there's plenty of resources online or on textbooks and things like that about the pinhole camera model. But for like basic information, I think the wiki page has a pretty good, easy to understand explanation and really nice diagrams as well. So I'm just going to use that to just kind of run through what really happens when you take a picture or record a video or whatever, right? So first let's look at this diagram, right? So this diagram really sets up all the important coordinate frames that we have to deal with, right? So when you're thinking about camera projection, there are two important coordinate frames or frames of reference that you have to keep in mind. One is this frame over here, the one that you can see that's defined by x1, x2 and x3, right? So this coordinate frame is defined at the aperture of your camera. That is this little hole where the lens is, where the light is coming from, right? So this coordinate frame is a physical thing, right? So it's related to the real world, right? So you can actually take any real world object and define it relative to that coordinate frame in 3D space. So imagine like a coordinate frame that's like being defined at your camera that can sort of be used to describe actual 3D point in space, right? So everything that you see on this side is the real world, right? And this coordinate frame is defined at the aperture of your camera. The second coordinate frame that you have to keep in mind is this, right? So this is what we call the image plane. So this is more of a virtual thing that's kind of like in your camera sensor or whatever, right? So this is where the projection of light that comes from the real world kind of projects onto either camera sensor or when we used to use film, sort of what do you call them, light sensitive film material or whatever. This is what it actually represents, this image plane. So what's really happening is you have a 3D point in space in the real world that's being projected through the camera's lens onto an image plane, which is usually either film or camera sensor when it comes to digital cameras and things like that, right? So there's a coordinate frame that's defined there as well, and that's the image coordinate frame. So what we're really going to study is how this 3D point that's out in space in the real world gets projected onto this 2D image plane, right? And understanding it is pretty straightforward because it's just a little bit of trigonometry, right? So what we're going to do is we're going to look at this image from the top. Imagine you're looking at this image from the x2 coordinate axis. So imagine you're looking at this from the top, and that's what's represented in this image. So you can see here that this point P is actually over here now. This x1 coordinate axis is actually here. This y1 coordinate axis in the image plane is actually here. And this projected point from 3D space to the 2D space is seen here, right? A couple of more important things before we move forward is the distance between this coordinate frame, which is a camera coordinate frame, and this image plane is what we call the focal length, right? F. And this x3 axis, the point at which it sort of intersects with this image plane, is what we call the principal axis. right? Or the principal point. So x3 is what we call the principal axis, and the point where it cuts the image plane or intersects with the image plane is called the principal point. And this origin over here in the camera coordinate frame is what we call the optical axis. Right, so imagine you're looking at it from the top, and what you get is basically this diagram, right? So we have the real world point here out in 3D space. This is the image plane, and this is where kind of the light ray intersects with this 2D image plane, and you get a projection, right? So think of it as like a shadow. You have a 3D object that casts a 2D shadow onto this image plane, right? So what we're trying to understand is this relationship between this 3D point and this 2D point in this 2D image plane. So what we can use is basically some simple trigonometry. So if you look at these two triangles, you can see that they share the same angle here, same set of angles here, a 90-degree angle, a common angle here, and that makes this angle also equal. So what happens then is both of these two triangles are what we call similar triangles, right? So if these two triangles are similar triangles, that means the ratio of this divided by this is equal to the ratio of this divided by this, right? So that's what you get here. So what happens is minus y1 over f is equal to x1 over x3, right? So minus y1 is over here, right? So y1 is basically in the image coordinate frame, right? And x1, x3 is out here in 3D space, right? So now we have this relationship that you can see here that relates y1, which is in your image plane, with 3D coordinates from your camera coordinate frame, right? And if you just rearrange the equation bit, you can get this equation, which is just saying that y1, which is on an image plane, is equal to f into x1 divided by x3. You do the same. So we derive this equation by looking from the top, right? By looking at the x2 axis. Imagine you looked at the x1 axis and try to get the second coordinate, that is the coordinate along the y2 frame. With this, it's pretty much the same argument. By using the same argument, we can get y2, which is your second coordinate on your image plane, using this equation, which is y2 equals minus f into x2 divided by x3, right? So that is basically how you get your projection equation. So if you put these two together in matrix form, you can easily get this equation, right? Which is y1 and y2, which is basically your image plane coordinates, is equal to f, which is your focal length, divided by x3, which is the distance from your camera coordinate frame to the object, and x1 and x2, which is all in the camera coordinate frame in 3D space, right? So you actually end up with this equation over here. Now you might be wondering, you can see that there is a minus over here, and you can see that what happens when you do this projection is any object kind of gets flipped when it gets projected. So if you have an object looking down, it will get flipped over here. If you have an object upright, it will get kind of inverted, right? So what cameras usually do is they correct that inversion. So when it actually gets projected, you probably have seen this if you do a simple like projection using a magnifying glass or whatever. You can see that the projected object ends up inverted or upside down, right? So what digital cameras and regular cameras do is they correct that inversion and give us an image that's upright. So when you correct that inversion, that's kind of tantamount to rotating the image by 180 degrees, which is why the final equation doesn't have this minus sign. You'll end up with equation that doesn't have that minus sign because you correct for that inversion. Another way of understanding how to correct that inversion is you can look at the lecture slides, and you can see that the diagram is slightly different in these lecture slides than the Wikipedia page. So if you look at page 30 on your slides, you can see that the image plane is actually placed in front of the camera center rather than behind it. So physically, the image plane is actually behind the camera's aperture, right? Like it's inside the camera. But if you place, like if you hypothetically place the image plane in front of the camera, you can see that the image ends up actually upright. So this is the point in 3D space. If you project it onto the image plane and kind of hypothetically place the image plane in front of the camera instead of behind the camera, you can actually get that upright image, and the math that you derive will give you the same equations, right? Which is this. This is the same equation that we derived before, right? Basically, the 3D point mapped to a 2D point in the image plane. In the Wikipedia page, it was x1, x2, x3. In your slides, it's x, y, z, right? And these are the two image points, right? So you can see here in page 23 as well, it's the same diagram. It's the same explanation. The coordinate frames are defined with different symbols. So instead of x1, x2, x3, that's x, y, z. This is the camera coordinate frame, which is defined at the aperture of the camera. This is the image plane. And instead of y1 and y2 that you saw in the wiki page, it's x and y in your slides, right? So these two are your image plane coordinates. This is your 3D point, and basically that's how the projection really works. Now for this to work, these equations to work, we assume that the principal point is right at the center of your image plane. But in practice, when we are looking at your image, we generally define the image coordinate axis to either be at the top corner or at the bottom corner, right? Just so that it becomes easy to index the image, right? So for example, here in this diagram, you can see that the coordinate axis is actually defined at the bottom corner, right? And when you load images to MATLAB, for example, you'll probably realize that the coordinate axis is defined at the top, right? So for example, 0.54 in your image will be somewhere around here in MATLAB, right? So the matrix is defined in a way where you're indexing the pixels from here in MATLAB, right? So when you're dealing with actual images, usually the image coordinate frame is somewhere in the corner here, right? Not at the center. But to deal with that, since we derive these equations with the coordinate frame at the center, which makes it easier to really derive these equations, what we do is we simply just offset this equation by where this principal point is relative to this coordinate frame, right? So all we have to do is just add px and py, assuming that px and py are the coordinates of the principal point in the image plane relative to this coordinate axis, right? So it's just simple translation. So this is the set of equations you would get if you didn't have a offset, right? And if you do have an offset, which in most practical cases you do, where the image coordinate frame is actually defined at some sort of corner like this instead of at the center, all we have to do is just do a shift, right? Again, once you take these equations that we derived using trigonometry and put it into matrix form, you will end up with something like this, right? And you can see that this is what we call a homogeneous matrix, which means we add a 1 at the bottom just to make the maths easy, right? Because if this line of math is not there, we can't actually do a multiplication, right, to get a 3 matrix over here, right? So what we do is we add a bunch of zeros and ones here to kind of make the math easy and end up giving us the correct multiplication. So what's happening here is it's this same equation, right, put into matrix form. So if you just do a little bit of math, you can understand how like if you multiply this out, you just get these two equations anyway, right? So what you're getting on your right side is the 3D coordinates defined based on the camera coordinate frame, which is defined at the aperture of the camera, right? And these are your 2D points that you're getting on the image plane. But since it's a homogeneous matrix, you end up with this third element in your vector. So to get your final answer, you have to divide all of this by z, so that this becomes 1. So you can see here, if you divide this by z and this by z, you actually end up with these two equations, right? So this is basically what we call your camera projection matrix, basically along with the principal point offset, that is your px and py being offset. So so calibration of your camera is basically finding these parameters, finding px, py, and your focal length and things like that, because your manufacturer of your camera might give you those parameters, but you can't guarantee that they're right, or sometimes you might not be able to get those parameters from the camera manufacturer. So you need to have a way of calibrating your camera and obtaining these parameters, which is your focal length, your principal points, and so on, right? So that's the task of camera calibration, because once you have these points, what you can easily do is take a 3D point in space and figure out where it maps onto your image, and also more importantly vice versa. Like imagine you only have a photograph, but if you have these points, you can reproject it back into 3D space and kind of figure out where it was in 3D space, right? So that becomes really beneficial in mapping and things like that for a robot, or at least like even obstacle detecting where a person is in 3D space, because ultimately the robot is getting 2D images and you need to be able to relate that 2D information back into 3D space, right? Okay, so there's a little bit more about transformations here. I'll allow you guys to read through that and kind of understand it. It's basically saying that there might be a third coordinate frame which is defined relative to the world or a map, so some sort of external coordinate frame to your actual camera. So then there'll be an additional transformation from your world coordinate frame to your camera, and then you'll end up with sort of a transformation chain like this, which is basically you have the points in the world that will be transformed to the camera coordinate frame, which is the 3D coordinate frame defined at the aperture of the camera, and then you'll use the other projection equations that we learned to project it to the image coordinate frame, which is a 2D coordinate frame. So you're ultimately going from 3D points to 2D points based off a coordinate frame defined not necessarily at the camera's aperture, but even if it's defined externally at a different point. Alright, so now that you guys have kind of a motivation for why we need to calibrate a camera, and hopefully an understanding of the camera projection, if you still don't really grasp it, just read through this wiki page really carefully, or look at some videos on YouTube, or look at some textbooks. It's really not that difficult to grasp once you sit down and really run through it, and it's a very important like fundamental thing to understand about cameras and how they work. Alright, so having said that, what we're going to do now is actually calibrate the camera and use a toolbox to calibrate the camera easily without having to kind of manually do a lot of calculations ourselves. So the camera calibration toolbox we'll be using has been has been put together by Caltech. So I've given a link to the calibration toolbox. You can see it here. So they have an OpenCV version as well as a MATLAB version. So you can use the getting started page. It just says go to the download page and download the toolbox, right? So what you need to do is download the toolbox to a particular folder in MATLAB. So you can see here that this is the toolbox. You unzip it in your folder and make sure that make sure this toolbox and all the calibration images which are provided on UTS Online are in same folder, and make sure they all get added to the path, your MATLAB path. So how you do that is, so I have everything in a folder called tube2. So I'm just gonna right click, add to path, selected folders and subfolders, and now all of these files inside that folder is added to your MATLAB path. Okay, so your toolbox is added, your calibration images are over here. One small caveat, your calibration images that we provided you with are in PNG format. So we discussed what PNGs are and JPEGs and so on last time, but the calibration toolbox doesn't read PNGs, so you need to convert the PNGs to JPEG, and I provided a small script to do that. It's not that complicated. All it does is it reads all these PNG files, and so using IMRead, which we learned last week, actually 2 weeks ago because of the quarantine, and then we use IMWrite to write that file back as a JPEG. So when you run this, it automatically reads all these PNGs and saves them as JPEGs, L1, L2, so on. Okay, so now that we have that and we've added the calibration toolbox, what we're going to do is all you have to do is just follow the instructions that have been given in this in your tutorial, right? So the first thing you need to do is read those image files using your toolbox. So you run calib_GUI, which will bring up the toolbox. So calib_GUI. So that should bring the toolbox up. There we go. And then you select standard, and then you select image names, and it says here enter base name that will read your base name for your images, right? So the base name for our images is I, and your suffix is 1 to 10, right? So all I have to say is I, and then it asks for the image format, and you can see that PNG is not in the image formats, which is why we just converted it to JPEGs. So you select J for JPEGs, and it loads all the images and displays them. Right. The second step is we need to select extract grid corners. So before we actually do that, I'll just explain what is actually happening very briefly in your calibration process, right? So how the calibration is done is you have this checkerboard pattern, right? So so usually this checkerboard pattern is something you would print, put on a board, and you would take images using the camera you want to calibrate. So since you printed this out yourself, you would know the actual size of these squares, right? Actual physical real world 3D sizes of these squares. So what this calibration toolbox does is it automatically detects these squares, right? And then you tell it the size of the square based on what you just printed out, and then it kind of knows the since you give it the actual size of these squares, it knows the physical distance between these grid points in this square, right? So it kind of has the scale and 3D information of the actual distances between the checkerboards, and then it has these 2D images, right? So what it does is it uses that information to run an optimization process to figure out what would be the best camera camera intrinsic parameters, your focal length and your px and py, that would give you those actual checkerboard sizes in the real world, right? So that's basically what we do and what the toolbox does, right? So it estimates the focal lengths and the principal intrinsic parameters of the camera based on the size of the checkerboard squares that you give it. So but the thing is, it's not a perfect it's doing an estimate. It's kind of optimizing and figuring out what's the best camera calibration parameters that would actually do the task of projecting those checkerboard checkerboard squares into the images that you provided. So what you do is you can run the calibration a few times and try to kind of refine your result. So how that happens is it uses the initial calibration parameters that it estimates, and then it reprojects these grid points back into 3D space, right? And sorry, the other way around. It takes the 3D points and reprojects it back to the 2D image based on the initial intrinsic parameters that you estimate, and then it looks at the error between the actual grid points that it detected and the grid points it reprojected back, and that's what we call the reprojection error. And what it does is it tries to find the intrinsic parameters of the camera that minimizes that reprojection error as much as possible, right? So that's basically a kind of very simple overview of the calibration process that's happening underneath. Again, you can read a lot more about this in this website that is given in question number 1. All right, so the first thing you need to do is pick out the grid corners, right? Because like I said, it's the grid corners that are used to kind of do the entire calibration. So you have to select this option called extract grid corners, right? And then it'll ask you how many images you want to do it for, and you can say all images. And then it asks what's the window size for the corner finder. Just leave that as default. And then it asks you whether you want to manually enter the number of squares or allow for automated system. So we'll select automated. And then what we need to do is we need to select the corner points of the grid. So this part is when this whole calibration process gets a little annoying, because if you screw up halfway through, you have to start all over again, the entire process all over again. So be careful when you're doing this step. Just make sure you don't accidentally click anywhere. Just make sure you be careful, right? So another important thing when you're selecting the grid points is make sure you select it in the same order. So if you select this grid point as your first grid point, you need to make sure you do that to every other image as well. So I'm just gonna show how you do this. So you select the 4 extreme corners of your image, and then it will ask you what's the size of each of the squares. So we provided that in your PDF. It says 30. So the size of one of these squares is 30 millimeters, right? So you say 30 by 30, and then it asks if there is an initial guess about distortion parameters. We don't really have one, so we're just going to say no. And then it will ask you to do the same for the next 9 images, right? So make sure you select this grid corners in the same order, and you do the same for the next image. So I'm just gonna do this. So you have to do this for all 10 images. Make sure you are careful when you do it. Once you extract all the corners on the images, what we're going to do now is run the calibration, right? So once you run calibration, you can see that you get your initial result. You get your focal length, your principal point axis, your principal point. You get also distortion and skew parameters, which help you use. They're useful in more complicated models of the camera that you can use to model things like distortion a little bit more complicated models of the camera than the pinhole camera model that we learned, right? So you can also see here the pixel error, which is the reprojection error I was talking about before. So what you can do is you can run the calibration again to kind of refine the final result. So what you can do is here it says reproject on images, and you can see what the reprojection errors kind of look like, right? So when you say reproject on images, you can see based on the initial it asks you how many images you want to do it for. You do it for all images, and now you can see the reprojection errors that are there. And what you can do now is run recompute corners, right? And it'll ask for Wnt X and Wnt Y again. You just say 5 and you say for all images auto, and then it recomputes the corners for the images, and then you can say calibrate again to run the calibration again, and what it will do is recalibrate the parameters, and you can see that the reprojection error has reduced when you do that, right? So usually running the calibration like twice is enough, because you also don't want to completely overfit it by reducing the reprojection errors, because the more you reduce reprojection errors, you're also discarding or not taking into account the sort of outliers and things like that, because you're trying to kind of fit it to try to reduce the reprojection error as much as possible. So just like twice or thrice should be more than enough, right? And a pixel error of like I'd say between 0.1 to 0.15 is acceptable. Okay, so now comes the important part. How do you use these parameters to actually project a point from 3D space to 2D space? So our 3D point is 8580, which is given in the camera coordinate frame, which is the coordinate frame defined at the aperture of the camera. And how do we project it to the image coordinate frame, which is the 2D coordinate frame, and get these two coordinate points on the image plane. So if you look at the script, you can see how the projection is actually done. It's basically the same equations that were given to you in your lecture, and we've just written it out in matrix form. So I just copy pasted the px and py values that were spit out from the calibration toolbox, and you can see here that there are two focal length values that are given here, which can be slightly confusing, but it's because, like I said, there are more complicated models of camera projection. So along with the distortion and things like that, you actually have kind of an asymmetrical focal length. So you actually end up with two focal lengths. Don't worry too much about it. You can see that they're very similar in length. So but when you're defining your transformation matrix, you can put fx and fy separately here as shown in this script, right? But this is basically the camera projection matrix, the K matrix here. Here you can see that we only have one f, but if you want to be a little bit more accurate, you can put fx and fy here. And then you have the 3D point, which is 8580, and since we're going to do this in homogeneous multiplied with a homogeneous matrix, I've added a 1 to that. I've also created an identity matrix of size 3 by 4 so that it actually gets these dimensions right. So you can see here it's a 3 by 4 matrix, and if I multiply this 3 by 4 identity matrix, which is what I does, so if I say I 3 4, what it actually does is gives me an identity matrix like this, right? So once I write I here and multiply it into K, because K is a 3 by 3 matrix, but we need a 3 by 4 matrix. So if I multiply this I 3 by 4 with this K matrix, which I'll show you here, yeah, you can see it's a 3 by 3 matrix, right? And if I multiply it by this identity matrix, I'll get a 3x4 matrix that I want, and then I multiply that into XCAM, and I'll get basically this vector, right? And for us to get the actual 2D coordinates, I'll have to divide this by the third value and this by the third value as well, right? Which is what I have done here. And then I will get our final image coordinate points. So that's basically everything you kind of need to know about calibration and camera projection. So if you still have questions, you can drop either Liang or me an email, or you can there's plenty of resources online as well, and just take the time to really understand what's happening in a camera projection geometrically, and then try and run this calibration by yourself and get used to the process of calibration, and then understand how you can take a 3D point and project it into a 2D image using the script. So that's really all there is to this question. Just try and practice, and there's more information about the calibration toolbox here as well. Good luck, and I'll see you guys next week, next Tuesday. Have fun. See ya.